Up to now, we have seen the different types of comparators. In this class, we are going to discuss about the Schmitt trigger. So, what is Schmitt trigger? We will see. A Schmitt trigger is a special type of comparator circuit with a hysteresis implemented, and it is used to avoid the unwanted triggering. A Schmitt trigger is also a comparator, but it is a special type of a comparator, so which has the hysteresis implemented. We will get to know what is hysteresis next. Okay, so the Schmitt trigger is a special type of comparator circuit. It is also called as regenerative comparator. Okay, it is also called as what? Regenerative comparator. It is one of the important name. The OPAMP Schmitt triggers are divided into two types. One is inverting Schmitt trigger, another one is a non-inverting Schmitt trigger. Inverting Schmitt trigger and non-inverting Schmitt trigger. First, we will see about the inverting Schmitt trigger. In this inverting Schmitt trigger, this is the circuit. Here you can say the op-amp is working in the inverting amplifier configuration because the VIN voltage is directly given to the inverting terminal of our op-amp, and the non-inverting terminal is given to the reference voltage. Here the reference voltage is automatically generating from the output voltage. Actually, it is not the feedback, it is generating the reference voltage at the non-inverting terminal of our op-amp. So V0 is the output voltage, and the plus VCC and minus VEE are the supply voltages in order to operate the op-amp. And here R1 and R2 forms the voltage divider network, which is used to generate the reference voltage at this node. This reference voltage will be generated by using the output voltage and this voltage divider format. Okay, so we can say the VIN is greater than V reference, then the output voltage V0 is equal to minus V saturation. So we already know the comparator output is always saturation, but only whether it is a plus V saturation or minus V saturation will be decided by the input voltage. Okay, so here the VIN is greater than V reference. What happens? The VIN is greater than the V reference. Minus voltage is greater, therefore minus V saturation will be the output voltage. Okay, whatever we have seen in the normal comparator circuit, this operation is also a similar. And the next thing, VIN is less than V reference. If the VIN voltage, which means that voltage at the inverting terminal is less than V reference voltage at the non-inverting terminal. Therefore, here which voltage is greater? The plus voltage is greater. Therefore, this plus sign will be assigned to the output. Therefore, output is equal to the plus V saturation. Okay. So, whatever the input greater, that sign will be assigned to the output side. Here VIN is greater. So, VIN has the sign of minus. Therefore, output is minus. Here V reference is greater, V reference is given to the non-inverting terminal, therefore output will be the plus V saturation, like that. Okay, and the reference voltage can be controlled by using the R1 and R2 resistors. If you want to change the reference voltage, we have to change any value of R1 and R2 based on our required reference voltage. So these reference voltages has been given as the plus V reference voltage, which means that when the output is in the positive V saturation. Okay, these reference voltage can be given as V0 into R2 by R1 plus R2. How it comes? Here the reference voltage is the voltage across the resistance R2, that can be given by applied voltage V0 into across the resistance R2 divided by the total resistance V0 into R2 by R1 plus R2. Okay, so here the plus V reference is equal to V0 into R2 by R1 plus R2. Here, in order to generate the plus V reference voltage, the V naught must be the positive V saturation, which is equal to plus V saturation divided by R1 plus R2 into R2. And in order to generate the minus V reference voltage, the V naught should be equal to the minus V saturation. Therefore, minus V saturation into R2 by R1 plus R2. Okay. If the plus V reference is the positive saturation, when the V naught is equal to plus V saturation and is called as upper threshold voltage VUT. Okay. So this plus V reference voltage is for the positive saturation voltage, right? This plus V saturation is occurred when the output voltage is in the positive V saturation, and it is called as upper threshold voltage VUT. Okay, this is very important. The plus V reference, when the output is plus V saturation, then that voltage is called as upper threshold voltage. Notation is VUT. Minus V reference is the negative saturation when the V naught is equal to minus V saturation and is called as a lower threshold voltage VLT. Okay, so when it come, minus V saturation is for the negative saturation output voltage minus V saturation. Okay, minus V reference will come for the negative saturation voltage minus V saturation. So that time this minus V reference is called as a lower threshold voltage. So in the Schmitt trigger we have the two threshold voltages. That threshold voltages are called upper threshold voltage and lower threshold voltage. Upper threshold voltage and lower threshold voltage. These two voltages, based on these two voltages, our output will change its state. Let us see, when the Vin is greater than the upper threshold voltage, output voltage is equal to minus V saturation. When Vin is less than the lower threshold voltage, then the output voltage is equal to plus V saturation. Same equations what we derived in the last, but instead of V reference, we just changed it as upper threshold voltage and lower threshold voltage. If the input voltage is greater than the upper threshold voltage, then only output voltage will be switched to the minus V saturation. If the input voltage is less than the lower threshold voltage, then only output will be switched to the plus V saturation. So when the input lies in between the lower threshold voltage and upper threshold voltage, then V naught will be in the previous state. So VLT less than Vin less than VUT, then the output will be the previous state, whatever the state, that will be maintained commonly. Okay, the difference between the VUT and VLT is called the width of the hysteresis. The difference between upper threshold voltage and lower threshold voltage is called width of the hysteresis. So the width of the hysteresis has been denoted by H. H means hysteresis. Hysteresis is also called the dead band, dead zone. Dead band, dead zone. In this hysteresis, no change in the output will occur. So what is hysteresis? It is a transfer curve drawn between the input signal and output signal. Okay, so when the input signal is lies in that hysteresis band, it won't change its output. Okay, that's why it is called as a dead band and dead zone. And this H is given as 2V saturation into R2 by R1 plus R2, because it is lies between the plus V saturation plus reference voltage to minus reference voltage. Therefore, H is equal to 2V saturation into R2 by R1 plus R2. This is the hysteresis curve. Here you can observe, on x-axis we have the input voltage Vin, on the y-axis we have the output voltage V0. Okay, so from this we can say, like, when the Vin is greater than the upper threshold voltage VUT, then only output will be switched to minus V saturation level. Okay, so we are starting from here. Our output is in the plus V saturation now. This output voltage will not change in this entire period. Only when the input voltage is greater than this upper threshold voltage, then only output will be switched from the plus V saturation level to the minus V saturation level. Okay, so when the input voltage is less than the lower threshold voltage, here why it is less than? Because it is a negative side. From 0 to it is the negative side. When the input voltage is less than the lower threshold voltage, then only output will be switched to minus V saturation level to plus V saturation level. So in between the VLT to VUT, lower threshold level to the upper threshold level, our output will not get changed. Only when the input voltage is greater than the upper threshold voltage, then the output changes from the positive V saturation to the negative V saturation, and when the input voltage is less than the lower threshold voltage, then only output voltage will switches from the minus V saturation to the plus V saturation level. Okay, so this is called as hysteresis, and this hysteresis means it is the difference between the upper threshold voltage to the lower threshold voltage, which is denoted with the capital H, and this H is equal to 2 V saturation into R2 by R1 plus R2, because so V reference voltages are upper threshold voltage or lower threshold voltages are same, which are occupied in the negative side as well as the positive side. That's why this negative side to the positive side we have two reference levels, 2 into V saturation into R2 by R1 plus R2. Now we are going to see about the second type of the Schmitt trigger, which is a non-inverting Schmitt trigger. This is the non-inverting Schmitt trigger circuit. So why it is called as a non-inverting Schmitt trigger? Because the VIN voltage is given to the non-inverting terminal of our operational amplifier, and the inverting terminal has been grounded. Here R1 and R2, which are forming voltage divider network. So at node VA, we will get the reference voltage, and the current flowing in the R2 resistor is IIN, input current for our operational amplifier, and this IIN is flowing entirely into the R1 resistor. No current is going into the op-amp because of very high input impedance, and V0 is the output voltage. So similarly, this is the hysteresis curve, and the upper threshold voltage will be given as IIN into R2. Upper threshold voltage is the voltage at the node A, that is equal to IIN into R2, which is equal to R2 by R1 into V saturation. R2 by R1 into V saturation. So that is equal to V saturation into R2 by R1. Similarly, the lower threshold voltage is equal to R2 by R1 into minus V saturation. Whenever the output is in minus V saturation, we get the lower threshold voltage. Whenever the output is in the positive V saturation, we will get the upper threshold voltage. Therefore, this VLT can be written as minus V saturation into R2 by R1, and the hysteresis is the difference between the upper threshold voltage to lower threshold voltage. Then is equal to 2 into V saturation into R2 by R1 resistance. So this is the hysteresis curve for the non-inverting Schmitt trigger. So here you can observe, if the input voltage is less than the lower threshold voltage VLT, then only output will be switched between the plus V saturation to minus V saturation, and when the input voltage is greater than the upper threshold voltage, output will be switched from minus V saturation to plus V saturation, which is exact opposite to the inverting Schmitt trigger. There input is less than VLT, the switching operation from minus V saturation to plus V saturation. Here the switching is from the positive V saturation to negative V saturation. Okay, like that, exact opposite to the inverting Schmitt trigger what we discussed in the last. Okay, so this is about the Schmitt trigger. Next, we are going to see about the square wave generator. In the square wave generator, the square wave generator using OPAMP means that the Astable MultiVibrator using the operational amplifier. So the Astable MultiVibrator can generate a square wave. So the Astable MultiVibrator does not have any stable states. It will automatically generate the square wave without any input signal or external trigger. So this is a circuit for Astable MultiVibrator. So here you can observe VN VP, the negative reference voltage and the positive voltage. So VP is the voltage given to the non-inverting terminal and VN is the voltage given to the inverting terminal. So from the output side to the input side, we are using one feedback resistor RF, which is given to the inverting terminal, and from the inverting terminal to the ground we have added one capacitor, and from the output of our op-amp to ground we are using one voltage divider network by using R1 and R2. So the voltage at the non-inverting terminal is equal to the voltage across the resistor R1. Therefore, the reference voltage at the non-inverting terminal can be given as V0 into R1 by R1 plus R2. Okay, like that we can given. When V0 is at the plus V saturation level, the feedback voltage is called as upper threshold voltage VUT and is given as VUT is equal to plus V saturation into R1 by R1 plus R2. Okay, already we have seen here the reference voltage is the voltage across the R1, V0 into R1 by R1 plus R2. Okay, that is the equation for the reference voltage. Here always the output voltage is in the saturation levels, we are assuming like that. So that's why one of the reference voltage is plus VUT, upper threshold voltage, which is equal to plus V saturation into R1 by R1 plus R2. When the V0 is at negative V saturation, the feedback voltage is called as lower threshold voltage VLT and is given as VLT is equal to RT into minus V saturation by R1 plus R2. So these two are the equations for lower threshold voltage and upper threshold voltage of a Astable MultiVibrator. So which uses like a Schmitt trigger. So this is the circuit. So when VUT is the voltage across the resistor R1 when the output is at plus V saturation. So I is the current flowing in the feedback resistor and the same current will flow into the capacitor too because the input current for op-amp is 0. So when you see the output is in the plus V saturation level, then what happens? This output voltage will go like this and then the capacitor will start charging towards the plus V saturation. From the 0 to plus V saturation, it starts the charging and this op-amp is working like a comparator. It is working like a comparator. Here one of the reference voltage is the voltage across R1 which is VUT which is equal to the plus V saturation into R1 by R1 plus R2. Okay, here is the VUT level. Therefore, the capacitor is charging right linearly. It is charging whenever the charged voltage, this capacitor charged voltage is somewhat little bit greater than the upper threshold voltage, then we can say here which voltage is greater here, the capacitor voltage. This capacitor voltage is nothing but the inverting terminal voltage. Inverting terminal voltage will be greater than the non-inverting terminal voltage whenever the capacitor charging voltage Vc is greater than the upper threshold level. Then what happens? As the negative terminal voltage is greater, output will be switches to minus V saturation. Therefore, automatically output will be switched from the plus V saturation to minus V saturation. Now, what is the voltage here? Lower threshold voltage will be there because here V0 is minus V saturation into R1 divided by R1 plus R2 will be the lower threshold voltage which is given to the non-inverting terminal. Now what happens? Output is the negative voltage. Therefore, the capacitor will start charging towards the minus V saturation. So up to now the capacitor has been charged up to VUT. From now it is going to charge towards the minus V saturation like this, negatively charging. And now when the capacitor reaches to VLT level, lower threshold value level, then what happens? That charged voltage is little bit greater than the lower threshold voltage. Then if the charged voltage is less than the lower threshold voltage, at that time the voltage at the non-inverting terminal will be greater than the inverting terminal, then the output will be switched from the minus V saturation to plus V saturation. Okay, because here if you observe, this capacitor is charging towards the negative. When the charged voltage is going to down means which is lower voltage than the lower threshold voltage. Therefore, we can say VLT is greater than the VC voltage. At that time, output will switches from minus V saturation to the plus V saturation. Whenever the output is the plus V saturation, again the capacitor will start charging towards the plus V saturation and it will charges up to the upper threshold voltage, and yet upper threshold voltage output will automatically switches to the minus V saturation and the operation will repeats. Okay, this is about the operation of the Astable multivibrator using the operational amplifier. So now we have to find out the frequency of oscillations because it is generating a square wave. What is the frequency of oscillations we have to get? The frequency of oscillations, the voltage across the capacitor as a function of time is given as Vc of t is equal to Vmax plus V initial minus Vmax into e power minus t by tau, where tau is the time constant. Vmax plus V initial minus Vmax into e power minus t by tau, where Vc of t is the instantaneous voltage across the capacitor, which means that the charging voltage of the capacitor, V initial is the initial voltage from where the capacitor is getting charged, and V max is the voltage towards the which capacitor is charging, up to which the capacitor is going to be charged. Not charged, going to be charged is called as V maximum level. So let us consider the charging of capacitor from VLT to VUT, where VLT is the initial voltage and VUT will be the instantaneous voltage, and the plus V saturation is the maximum voltage. Let us see from the diagram. So now we are assuming that this capacitor is charging from the VLT to the plus V saturation. Here the VLT is the initial state and the final state will be the V saturation, but it was getting stopped at the upper threshold level. That is fine, but the final state, actual final state should be the plus V saturation. Okay, at the time t, it is going to charge up to VUT only. That is what we are going to show in this derivation. So at the time t is equal to T1, the voltage across the capacitor will reaches to the VUT level, upper threshold voltage level, and therefore the equation 3 can becomes VUT upper threshold voltage, because at the time T1 it is at the voltage of VUT. So VUT is equal to plus V saturation, the maximum level, plus initial level VLT minus the maximum level plus V saturation into e power minus T1 by RF into C. RF into C is a time constant of this Astable multivibrator or square wave generator. Therefore, if you write only this equation, minus of VLT minus plus V saturation into e power minus T1 by RF into C is equal to plus V saturation minus VUT. Now, if you write only e power minus T1 by RFC is equal to the plus V saturation minus upper threshold voltage divided by the plus V saturation minus lower threshold voltage. Therefore, the minus only this power value can get by taking the ln natural logarithm on the both side. So, if you take ln of E, so ln and E will get cancelled. Therefore, we will get minus T1 by Rf into C is equal to ln of plus V saturation minus lower threshold voltage divided by the plus V saturation minus lower threshold voltage, here upper threshold voltage. So, T1 is equal to minus RFC into ln of plus V saturation minus upper threshold voltage by plus V saturation minus lower threshold voltage. It is the equation for half of the time period of the square wave or that capacitor charging voltage time period. So, which is equal to RF into C ln of plus V saturation minus VLT by plus Vsat minus VUT. The time taken by the capacitor to start from upper threshold voltage to the lower threshold voltage is same as the time required for charging the capacitor from VLT to VUT. Therefore, the total time required for one oscillation is given as, okay, this is the time for only the charging from VLT to VUT. Similar time, the same time will be taken to charge from the VUT to VLT, reverse charging. Okay. Therefore, the total time is equal to T is equal to T1 plus T1. Therefore, T is equal to 2 T1 and which can be written as 2 into RF into C ln of plus V saturation minus VLT by plus V saturation minus VUT. The frequency of oscillations can be determined by f naught is equal to 1 by t. We already know frequency is equal to 1 by time period, where t represents the time required for oscillation, which is equal to this one, right? Therefore, by substituting the value of t in the above equation, f naught is equal to 1 by 2 RF C ln of plus Vsat minus VLT by plus Vsat minus VUT. This is the frequency of oscillations of a square wave of the Astable multivibrator, and substituting the value of VUT and VLT, we can get that tau, the time period, is equal to 2 RF C ln of plus Vsat minus R1 into V saturation by R1 plus R2. So, here we are substituting the value of VUT and VLT. It is a VLT value and this one is a VUT value. R1 into plus V saturation by R1 plus R2. Okay. Therefore, if magnitude of plus Vsat and minus Vsat are equal, then we can write T is equal to 2 RFC ln of plus Vsat into 1 plus R by R1 plus R2 divided by plus Vsat into 1 minus R1 by R1 plus R2. Okay. So, here we have just taken the V saturations as common. Therefore, these two V saturations will get cancelled. Thereafter, the equation can be simplified as T is equal to 2 RF C ln of 2 R1 plus R2 by R2. This is the total time period of the square wave generated by the square wave generator. Okay, if you take f is equal to 1 by t, then you can get the frequency of oscillations too. Therefore, the frequency of oscillations f is equal to 1 by 2 RF C ln of 2 R1 plus R2 by R2. Like that we will get